Good evening, everyone. If the audio and video both are fine, please let me know first. All good? Wonderful. Right. So let's begin with our session. Sorry for the delay. There was something that I really got stuck with and could not make it on time. And in this city, it takes a lot of time to travel, even smaller distances. All right. So first, what we'll do is we had completed our first chapter, that is energy, and we had discussed various aspects of it, and some of the questions in the prelims examination that have been asked in the past papers. Now, before we go on to our next chapter, that is space technology, we'll discuss some of the questions that have come in the mains examination. So, in the recent past, we see that there are four important questions that have come from energy chapter. Although there is another chapter that another question that had come in geography paper incidentally regarding wind energy, and again the answers are pretty similar to what we have already discussed in our classes for wind energy here in science. Now, when we look at these questions, if you look at the first question says, do you think India will meet 50% of its energy needs from renewable energy by 2030? Justify your answer. How will the shift of subsidies from fossil fuels to renewables help achieve the above objective? Explain. Now, uh, there are certain aspects of this that you need to understand. And the first question, if you see, first part of the question says that do you think that India will meet 50% of its energy needs from renewable energy by 2030? Now, if you remember, we had discussed, and when I discussed the data with regards to renewable energy, we had discussed there that 50% of the electricity that we produce right now, by 2030 we want that it should come from non-coal, non-petroleum sources. So the question asks the same, that do you think that's possible? Now, when you get questions like these, the answer is not a yes or no. You cannot say that yes, thinking that okay, government will reward you for writing yes, and you can't write straight away no, because that's not what you're supposed to do. So you have to be balanced, you have to be objective in writing answers to these kind of questions where your opinion has been asked. Now, just understand that when a question says that in your opinion, or do you think, what do you think, what is your opinion, what is your take on it, in all of these cases when you give your opinion, it need not be your opinion, that is your personal opinion, but opinion which is based on what you have read, what some of the experts have said, what some of the most known people in this matter have said, or what the data says. So it should not be just a personal opinion or a personal insight without having a very strong backing for having that opinion. So when you say, do you think India will meet at 50% of energy targets? Don't just start with a yes or no. That, oh, yes, I think that India will definitely do it and all that. And you cannot say, no, no, look at what's happening. It's not possible. India can't do it. You cannot go an extreme way, whether yes or no. You have to talk about what's happening in the present. What are we doing right now? What are the plans that the government has? And how do you think that, if possible, what is the roadmap that leads us to 2030, that leads us to 2030 with 50% of the energy targets being met with the help of renewable energy sources? So in this manner you have to do that. All right, you'll have to think in this manner instead of just writing a yes or no, or just writing a personal opinion in these kind of scenarios. So for example, when we start writing this answer, how do you introduce this? So first you have to understand that there are two parts to this question, right? This is part 1, and then this is part 2. How will the shift of subsidies from fossil fuels to renewables help achieve the above objective? Explain. So this is the second part of the question. Now overall you have 250 words. So first you have to think of the breakdown, what the breakdown should be. First, let's say 20 to 30 words should easily go to writing an introduction. Then after that, there are two parts to the question. So part 1 and part 2, and then you have the conclusion. So conclusion, or the way forward, depending on the question's demands, will take another 20 to 30 words. So in a manner, you are left with 200 words, meaning that you can give almost 100 words to part 1 and you can give almost 100 words to part 2. Part 1 and part 2. Now, this is a thought process that you need to build anytime you think of writing an answer. Every time you get any question where you have to write an answer, depending on the number of words that you have, whether it's 150 or 250 or whether it's an essay. So, whatever it may be, first you have to think that, okay, this is what I want to write, this is how I want to approach, and these are the things that I can write. So, when it comes to the introduction to a question like this, what will we do? First, we'll talk about renewable energy and the present scenario. All right. So, renewable energy plus the present scenario, and you can talk about some of the data points that we have right now, and then coming to, because that builds up to the first part of the question anyway. So now you have to write that, okay, this is what the target is, because you have to give the context that why this question has been asked. So you have to talk about that context, that the government of India has taken a pledge that by 2030 50% of the electricity production or 50% of the energy needs of India will be met by non-coal, non-petroleum sources. Now, to do that, what are we doing? So then you can list out all the schemes and policies that we have the National Solar Mission. Now we have the Suryodaya scheme, and now we also are building solar parks. Then there are innovative solutions like uh, 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 rooftop solar, which is the Surya Ghar scheme, or we have this floating solar power plants that we are building everywhere. Then plus there is this solar tree which is being built by CSIR. So then you can write all that, plus we have the wind energy policy. What is the national wind energy policy, plus what is the offshore wind policy, what is the wind solar hybrid policy? There are so many things to name, there are so many things that can be written. And then biofuels, because biofuel is where we are doing better than the targets that we had. So what are we doing in biofuels, how the national biofuel policy is important, what is the uh, uh, PM Jivan Yojana. So there are all these things that you can list out, that these are the things and these are the roadways to looking into the renewable energy future. And then the green hydrogen mission, that as a part of the green hydrogen mission, how exactly do we want the various industries to take shape and uh, take help from green hydrogen and start using green hydrogen as an alternative fuel. So these are the various things, these are the various objects that you can use in writing this first part of the answer. And that's why this is one part that can take a lot of time. So even if, let's say, for example, it may so happen that you have more points with regards to part 1 as compared to part 2, then extending a little further in part 1 than part 2 is also fine. There's no problem with doing that. That instead of writing 100 words, even if you go to 120 or 130, it's okay, you can do that. And then this reduces to maybe 70 to 80. So that's okay, that's fine, you can do that. Because if you have a lot of points that you can enrich your answer with, fine enough, use that. So you have to all do all that, and you have to put all these numbers and data and about the policies and the schemes. And then on the basis of that, you can basically say that we are, in a manner you can write that we are in a on a right track to achieve these required targets. So you can do all that in writing the first part. Now the second part says, how will the shift of subsidies from fossil fuels to renewables help achieve the objective? Now when you give subsidies to something, giving subsidies means what? That in a manner you are providing a financial help, correct? You are helping them financially by providing those subsidies. So when we provide subsidies to any scheme, any policy for that matter, then what happens is that by providing that subsidy, we are able to provide a financial help to it. So now if the shift of subsidies happen from fossil fuels to renewables, then a lot of growth in renewables will be seen, that we will have better money, more money to spend on renewable energy and the innovative technologies that help renewable energy. At the same time, we'll see that the entire private ecosystem also will start shifting. So for example, let's say the companies that are getting help because they are in the coal petroleum sector, if they stop getting help from the government there, and the government starts focusing more or diverting all the money towards solar and wind energy or biofuels, many of these companies would also want to move towards wherever the subsidies are. because they know that they are getting that financial help to grow further. And we see that a private ecosystem also starts building in that sense. So it's not only the government money that starts flowing and the entire sector that starts building, but at the same time the private sector also starts building up in these kind of areas. So that's why in a manner it will help in shifting of our economy, which is based on coal and petroleum largely, to shifting it to solar, wind, or biofuel, etc. based uh, model. So that's why this also becomes very, very crucial in enhancing the amount or enhancing the overall participation of renewable energy in the sector. So you can write all that, and then lastly, while concluding, you can say that uh, with all that given, with all these things that are already in place and what the government of India is doing, it will definitely help in building things further, and we are in the right direction to get to the targets that we have kept for 2030. So this is how you can basically conclude your answer and write it in a structured manner. Then question number two talks basically about blue LEDs. And for blue LEDs, Nobel Prize of 2014 was given. So how this invention has impacted everyday life of human beings is what the question is, and again in 250 words. Now, overall when it comes to these schemes, or let's say when we talk about the blue LEDs, first you have to talk about the basic introduction. You can simply put forward the same thing that today we have seen a lot of advancements with blue LEDs, and that's why it notably also got a Nobel Prize in 2014. Now, how is it helpful? Then you start writing about everything. So, for example, you can talk about electricity, that how in electricity it plays a big role. How exactly? First thing, the longevity of LEDs. Blue LEDs, basically everything that you are using, every LED that you are using, the white colored light is basically blue LED. So blue LED for electricity, how exactly it is helpful in electricity? Because of its longevity, first of all, that it lasts very long compared to incandescent bulbs or the fluorescent light. Compared to them, they last very long. Then at the same time, they also help us in energy saving, because they do not use as much power as your bulbs or tube lights, etc. would use. So they draw less power, they give you a good longevity, and they have a good power efficiency altogether. So that's why they overall will be very, very helpful in power saving. And that's why they can help in help economically as well, that they can bring down the electricity consumption in the domestic and industrial households, I mean domestic households and in industries as well. So there are all these things that we have in electricity. Similarly, there are other sectors in which blue LED has played a big role. All your screens, the screen, for example, on which you are watching this lecture right now, whether it's a mobile phone or a laptop or whatever it is, this also is what? This is also blue LED. The screen is being lighted up with the help of blue LEDs. So that's why blue LEDs have played a major role in uh, electronics as well. The television screens, also the LED television screens, are also blue LEDs. So that's why blue LEDs have been very, very helpful in electronics as well. Then at the same time, in the health sector also, they've played a big role. In the health sector also, there are medical procedures where LEDs are very, very useful, and that's why we have seen that in medicine also LEDs help. At the same time, they also help in agriculture. We have seen that blue LEDs can be used as a source of light that is required for the growth of plants, and that's why in many of the cases you'll see that ultraviolet light is used, or they make the use of LEDs, etc. also to enhance the overall productivity in the crops as well. So that's why we see that there are a lot of ways in which blue LEDs have played a big role, and that's why it has definitely impacted the everyday life of humans. So there are all these points to be written. Now the next two questions, if you see, these are questions both of them related to nuclear energy. And nuclear energy has always been one of the favorite topics of UPSC, that every now and then they keep asking questions on nuclear energy, whether in the mains examination or in prelims examination. Every second, third year, one question does come, and it's more often than not that you'll find that there will be a question either in prelims or in mains, if not both. So that's why this always has been a very, very important topic, and not only the last 5 6 odd years, but I would say if you go back and see the last 35, 40 years of question papers also, you'll find that every second, third year, one question on nuclear energy does come. So look at the question first. With growing energy needs, should India keep on expanding its nuclear energy program? Can the answer be no? Can you say that, okay, India's energy needs are growing, but India should stop using nuclear energy? We can't say that. And that's why the second part of the question, discuss the facts and fears associated with nuclear energy. Basically, all the positives and all the negatives. So, positives wise, we know about a lot of things, that how nuclear energy gives us a huge amount of power. For the electricity sector, it is going to be very, very crucial. Then we are right now trying to also build upon nuclear fusion, and nuclear fusion for the future can be very, very crucial. So you can write about all that, you can include all these points in your answer. Then the problems of nuclear leakages or the meltdowns and nuclear accidents, where we always have had a lot of fear with regards to nuclear energy and the radiations, and if radiations can be harmful. So we do know that radiations can be harmful, and that's why we need to take all the safety measures possible to ensure that these do not affect human life. At the same time, the nuclear waste or the radioactive waste, the radioactive waste generation and how we dispose the radioactive waste is also very, very crucial to understand. So whether it is about high level waste or low level waste, meaning the radioactive waste or all the non radioactive waste that we are producing. So understanding all that and understanding how they can also be very, very crucial uh, in making this nuclear energy safe. So you have to talk about both the aspects, but you have to give a way forward, and you have to give a way forward, and the conclusion in this answer, remember this, that conclusion needs to be positive. Conclusion needs to be positive. And also, because you are discussing the positives and the negatives here, make sure that the positives are more and the negatives are less, that your positives are occupying more space and the negatives are occupying less space. So always take care of that also while writing these kind of answers. It should not look like that you've completely gone on a negative side, because we know that nuclear energy is going to be a big part of energies in India's energy future, and governments will always want to tap into nuclear energy. We know the potential that India has with nuclear energy. So it's not that the governments are going to uh, give in and they are not going to work ahead with nuclear energy. They are always going to spend a lot of money in making nuclear energy a possibility, and especially the thorium based nuclear energy, where India wants to move with India's three-stage nuclear program. So that's why always remember this. Then, give an account of the growth and development of nuclear science and technology in India. What is the advantage of fast breeder reactor program in India? Simple. First question is directly about India's nuclear program. So you have to talk about India's nuclear program. So you can very easily define the three stages of the program that we discussed. So first part is about India's nuclear program, and then the second part is simply about fast breeder reactor, and we discussed about fast breeder reactors, that how fast breeder reactors will give you more energy or more material to work with, and that's why amount of byproducts are more than the amount of reactants that we have used. So that's why it can build a future for a very, very long time, and that is why we are so much focused on fast breeder reactors. So that is basically what you have to write in the second part of the answer. So these are some of the questions that have come. So that's why just remember that, and if you see that these questions that they have asked, these questions are not very difficult to answer questions. That's what I said in the first class also, while we were discussing the strategy for science and technology, that science and technology as a subject at prelims level can be more difficult than in the mains examination. In the mains examination, the questions are easier compared to the kinds of questions that we see in the prelims. So that's why your preparation has to be better for your prelims examination. And in the mains examination, questions will largely be static in nature and will be picked from areas which are very visible areas. They'll not pick areas which are not visible or that we do not know of. So that's why just take care of these things from a strategy perspective. So any question from here? The second question, the Rani, you have asked this question. The second question is asking about 2014. Was it in the news in 2021? No, it was not. And okay, so one very, very important thing actually about this question, that when this question was asked in 2021 paper, uh, I saw that there were a lot of analysis being done on YouTube by uh, others, other institutes also, where some of them have very wrongly put something up. And a couple of people discuss that, look, I have been telling you that you have to know last 10 years of current affairs. That's very, I don't have the right words to say, but this is wrong strategy. This will be a very wrong strategy if somebody starts to follow. You really can't read last 10 years of current affairs. That's impossible to do. And if you are really planning to do that, start preparing for 2029. It's impossible that you can read last 10 years of current affairs, and that's impractical also. That yes, a couple of questions will always come from something that is beyond 1 year, or maybe beyond last 18 months, but that's okay, let that come. Because you have to look into the return on investment, that can you invest so much time on last 5 years of current affairs or last 3 years of current affairs without compromising on all the GS areas? You can't. You will compromise somewhere. Otherwise you'll start preparing for 2 years after whatever your target year was. So please don't do that. And about this question was asked in the context of LEDs, because LEDs now have become a part and parcel of our lives. It was not specifically in news in 2021, just that how LEDs have grown in the past few years, especially since 2015-16 in India, when the government of India had the Ujala scheme, where they started distributing LEDs for free in the rural areas. And you'll see that the LED prices, or the LED lights that we are using, the prices of LED lights drastically started to fall because of some policy shifts that we saw in India. So that's why it started becoming a part and parcel of our lives. So no, it was not specifically in the news, but just that it now has become such an integral part of our lives. And one of the three parts of your main syllabus says science and technology in everyday life. And that's the context, I would say, why this question was asked. Yes, Homo, you have a question. If I write it in a way where I give the roadmap first, then give my opinion, like it is possible or not, based on the roadmap I've written previously, it's very difficult because you will be wasting some words in just defining that. So that's why the roadmap for your answer should be built always in a rough or in your mind instead of being in the paper. So that's why don't do that, because then you will have less time to, or less time and also less words to write the actual answer. Is this data correct that USA has 21.4% of total from renewable energy, where India has almost 30% more than the US? Depends on how you are counting the 21.4%, because huge amount of US energy resources, they actually are coming from natural gas based resources or methane based resources. So that is one of the things that actually add to their. But overall, when you look at some of the aspects of renewable energy plus also nuclear energy, because there in their mix nuclear energy plays a very big role. And nuclear energy typically we don't count as renewable, we count it as non coal, non petroleum. So there, when you add nuclear energy to this 21.4, then it takes a very significant number. Otherwise in India, for example, nuclear energy right now is just 3 to 4% of our electricity needs, whereas in case of US you'll see that it almost amounts to 15 to 20% or even more in certain areas. So that's why when you add that, then in that case you can say that they are doing good from that perspective. Where do we know where do we come to know about these schemes, means where do I get the source about the scheme? See, Shamila, in this case, there are two aspects that you can use. One can be the PIB, because PIB will always keep on mentioning any new scheme that comes in. You will see that PIB will always be mentioning it. So various ministries, they will keep on posting it. The second source, there is a website called as Vikaspedia. Now, Vikaspedia is a website where you will find all the schemes, and all these schemes, whatever new schemes come up, uh, they would keep it sector wise and ministry wise. So that also can become a very good source to uh, read about any scheme. Then Prabjot, you have asked, but blue LEDs are harmful for eyes. Cannot say that directly. See, overexposure to any kind of light source is bad. So, in that sense, you can say that. Or there are some aspects of blue LEDs and how blue LEDs can uh, have some negative impact on certain hormones and how they have been studied. But everything, when we talk about all this, it's overexposure, that if you are getting overexposed to these sources, then only, and you are very close to the sources and getting overexposed to a lot of intensity of blue LEDs, so then in that case, not only blue LEDs, any kind of light source can be harmful. And Deepshika, you asked, fear of proliferation can be written. Yes, of course, that is one of the fears that we have here. So yes, that's a very important point to write. Cheshta, Chetsa, sorry. I always have opposite. My negative points are always more than positive. Then you do questions from current affairs also come? Yes, they do come, and in every paper they come. In science, they can. In environment, in IR, in polity, in economy, in all these subjects, you can expect questions based on current affairs in the mains examination also. I have difficulty in writing conclusions. Kindly guide. So, conclusions, see, there are two types of conclusions that we often write in an answer. Either you summarize everything that you've written, that on the basis of everything that you've already presented in the answer, just give an outlook of that and end your answer, but try to end on a positive note or with a way forward. That even if you, let's say, have been criticized, remember this, that why I've been focusing on writing a way forward or writing a positive conclusion, because you, when you become a civil servant, you are supposed to solve problems and not just talk about it. Let's say you become a district magistrate somewhere and there is somebody who comes with a problem to you, so you cannot just discuss the problem with them, that they'll say that, sir, I have this problem, ma'am, I have this problem, this. You say that, yes, yes, I understand that you have problem, thank you very much. You can't do that. You'll have to provide solutions to all that problem, right? So when it comes to providing solutions, that's why when you write answers, it should show in your answers as well, that you are here to provide solutions and not just discuss the problems. And that's why your way forwards or your conclusions have to be positive. It's not because there is somebody who's sitting who is from the government and they'll not like it if you write a negative conclusion. That's not the case. It's because you are the ones who are going to be problem solvers tomorrow, so that should reflect when you are writing these answers as well. So that's why when you write conclusions, there are two things that should always try. Either just summarize everything that you have done if you are not sure about how to write that conclusion, or if you have a way forward, write a way forward, write about a future, etc. So that is another way to write conclusions. How to switch batches? I think it is there in the app. I'm not very sure how to do that. The notes want to be written in the examination. Should it be from the books or can we write in our own way? You can write, and you will have to write in your own way, because you will not remember the exact words from whatever is there in the PPTs or the notes or in the books. You will not remember them. So it will always be in your own words, and you should inculcate a habit where you start writing everything in your own words. Do we write more than 250 words? Absolutely not. Because if you look at the instructions given on the question paper instruction says not more than 250 words. So you cannot exceed 250 words. Ensure that you are in the range of maybe 230 to 250. If you go to 260, 270, nobody will bother you. But your 250 should not become 300 or 350. That is something that you'll always have to ensure. And this is where the practice becomes very, very crucial. You have not covered art and culture, environment and ecology, medieval, ancient. Should I appear this year or not? See, I would still say that you have time. That out of the subjects that you have listed, at least a couple of them can be finished. So please do that. Revise everything else that you know. See, nobody can ever be 100% prepared. You talk to seniors who might have given the examination last year or last to last year, they'll never say that they are 100% prepared now. If you have filled the form, maybe you can take a decision 2 3 weeks before the examination based on how well you are prepared. If you feel that out of all the subjects only couple of subjects are left and most of the other subjects uh, you have done well already, then you can give it a shot and you should not wait for the next year. Proliferation means, it means in simple words, weaponization. Less availability of uranium in India can also be one of the fears. Yes, Kushi, it can be, because then we are not energy secured and we have to be dependent on imports. So you can write it as a negative point. These types of these types of mains PYQs look more or less similar in environment and ecology as well. Yeah, they do. I mean, science and environment are very similar subjects in that sense. Even I would say geography is also very similar. You'll find a lot of questions in geography which a faculty might have taught you in science or in environment. These three subjects are related. Even in certain cases, even in economy, there are certain technological aspects that come in. So many of these subjects, they will have this kind of overlap. So yes, similar kinds of questions do come. At least how many answers we practice per subject? It should not be per subject but rather per chapter. That every chapter that you read from every subject, you should practice something from there depending on the length of the chapter. It's a big chapter, it has a lot of topics, then there are more areas to cover. And if let's say it's a small chapter, not a lot, then a couple of areas to cover. So it depends on the chapter, but every subject, every chapter, you'll have to do it. Hmm. In stage two, we use thorium, but thorium is getting from uranium. So, what is the win? No, we are not getting thorium from uranium. Why would you say that? Thorium reserves are there in India, especially Kerala coast has a lot of thorium, one of the biggest reserves of thorium in the world. So, we are not getting thorium from uranium. We are actually converting thorium into uranium. Thorium basically is getting converted to uranium 233. If we fill the form but do not appear in the examination, will it be counted as an attempt? No, it will not be counted as an attempt. Somebody who goes to the examination hall, that is counted as an attempt. Filling the form is not counted as an attempt. All right, so let's move to our next chapter, and this is space technology. Now, overall, when it comes to space technology, I would say is the most important chapter with regards to the kinds of questions that come and the number of questions that come, whether in prelims examination or in mains examination. I don't remember any year when in the prelims examination a question which is directly or indirectly based on space technology hasn't come. At least one question, if not two or three or four at times. So we have seen some years where in one single year prelims examination has had 3 to 4 questions only from this one chapter of space technology. So that's why it makes it not only one of the most important chapters in science and technology, but rather one of the most important subjects in the prelims examination. Because I don't believe that apart from maybe fundamental rights in polity being one more such chapter, where every year at least one question in directly or indirectly does come. So that's why space technology becomes one of the most important chapters for this entire prelims examination, because this is one chapter which almost gives a guarantee that every year at least one question will be asked, if not more than one, if not 3 or 4 questions. Now, many of these questions you'll find that in prelims examination, many of these questions are based directly on the static areas. We'll discuss a lot of those questions, and there are some questions which are asked as current affairs, which can be very recent current affairs, or also some current affairs which have been in the news for a very long time. So that's why we see that it has been a mix of static and dynamic areas. So we'll discuss all those questions as we move on. And in the mains examination, again, you'll find that questions are asked from pretty visible topics. So visible either in the static sense or even visible topics from the dynamic sense. So for example, right now, if I talk about this visible topics in space technology, you can simply say Gaganyaan mission or Aditya L1 mission. So these are missions which are very visible topics. So that's why they can ask questions from these kind of areas, and they can ask on India's program or India's policy and whatever India is doing altogether. So space technology, what we are going to do is we are going to divide this chapter into two parts. The first part is more important for the prelims examination, and the second part is a mix of prelims and mains. So first part is where we are going to talk about the universe, the various concepts related to the universe, and our understanding of the universe. And then after that, we'll go to space technology, where we'll discuss about satellites, their applications, and how India is faring in space technology and all that. So we'll discuss all this in the second part. So first, to start with, we are going to discuss about the universe. Now, about the universe, when we discuss, first thing uh, is about how exactly do we even define the universe. That if I ask you what is universe, how do you define the universe? What in your sense, what is universe? Can you say this? Can you tell me this? In your understanding, if you had to define the universe in one sentence, how you would you do that? How would you define the universe in one sentence? Collection of galaxies. Okay, fair. Endless space of cosmic energy. Fair point. Everything around us. That's great. Everything that exists in space and time, including all matter, energy, space, and time. Good. So, more or less, as a lot of your answers say, we are talking about everything. Correct? That everything basically is a part of the universe. And that's true. And that's why one of the simplest definitions that has been given, and this was given by uh, a scientist in the US who was associated with the US Defense and also NASA, Alexander Bolonkin. And he had given this definition: everything that exists, everything that has existed, and everything that will exist is all a part of the universe. So, simplest of the definitions that you can think of, but it actually defines everything that is there. Because how do you define something that is undefinable, that has no limits, that we do not know where it starts and where it ends? So, then in that case, this is how a better way to define it would be that everything that exists, everything that has existed, and everything that will exist is also a part of the universe. Now, I understand that, and as some of you had written also, that everything that exists is a part of the universe. So that is fine. But why are we also talking about the past and the present? Sorry, past and the future. That everything that has existed and everything that will exist is also a part of the universe. Now, this is where something very interesting, and something that in the lower classes, somewhere you might have read about, or if you remember, the law of conservation of energy. Do you remember this? Anyone who can tell me what law of conservation of energy says? Yes, Malikandan, the first one to give the answer. Energy can neither be created nor destroyed. Correct? So this is what it says, that energy can neither be created nor destroyed. It can only be transformed from one form to another. Correct? It can only be transformed from one form to another. So you cannot create new energy, you cannot destroy energy. You can only transfer energy, or you can transform energy. So these are the only things that we can do. That you cannot create new energy, but you can generate energy from something which is already existing. So this is where you can say that what existed, basically, let's say a star, for example, a star that existed maybe millions of years back, and now it has already run out of its fuel and it has been destroyed. But the light of the star still probably reaches us, because the light of the star might have taken millions of years to reach, and that's why the light of the star will take millions of years for it to stop reaching the earth. Similarly, even if it has been destroyed, it does not mean that it has ceased to exist or it has vanished. It has just transformed into something. A lot of particles have been emitted. A lot of neutrinos, for example, have been emitted. So in that case, it's not that it's gone or it's completely vanished. It's just that it has created something new. It has been transformed into something else. And similarly, everything that will exist, something today is just a ball of dust and gases, tomorrow can become a star, tomorrow can become probably a planet. So there are all these new creations which will keep on happening. But these are not creations, but largely these are transformations, that something has converted to something else. So that's why creation, this law of conservation of energy, basically is defining this entire system that exists in this universe. Now, overall, when it comes to the universe, if you understand the composition of the universe, we see that it has three parts: dark energy, dark matter, and the rest. Now, what is dark energy and what is dark matter? We'll try to understand that a little later. Let me first start with the rest. So, dark energy is supposed to be almost 68% of the universe. So, 68% of the universe is only dark energy, 27% of the universe is only dark matter, and the rest constitutes only 5%. The rest constitutes only 5%, and that too, out of that 5%, 4% is only free hydrogen and helium. 4% of the universe is only hydrogen and helium. So a lot of hydrogen and helium in this universe, freely existing hydrogen and helium, makes up 4% of the universe. Then apart from that, when you look at the last 1%, all right, so out of this 5%, 4% is only hydrogen and helium. When you look at the last 1%, 0.5% out of it is just all the stars in this universe. All the stars, the billions and billions and billions of stars that we have in the universe, they form just 0.5% of the entire universe. How many of these stars do you see? Maybe if you're living in a big city or a metropolitan city, maybe 10, 20 at max, maybe. And if you're living, let's say, some areas where light pollution is not that high, then maybe 50, 100 out of billions and billions and billions. So what you see is not even a tiny fraction, it's a negligible fraction of what exists. So all these stars, they just make up 0.5% of the universe. So it makes up just 0.5%. Then we have 0.3% are all the neutrinos. 0.3% all the neutrinos. So when we say all the neutrinos are making up 0.3%, what do we mean by neutrinos? Neutrinos, basically, neutrinos, these are chargeless and almost massless particles. All right, chargeless and almost massless particles, meaning that these are particles which do not carry any charge, and they carry very, very, very low amount of mass. That's why negligible amount of mass. So for that's why we, generally speaking, we also say that these are chargeless and massless particles. But they cannot be massless, they have negligible mass, they have very, very, very minuscule mass, but they do have mass. So chargeless and almost massless particles, and they make up 0.3% of this entire universe. And because of the fact that there are a lot of natural processes that lead to the creation of these neutrinos, the formation of these neutrinos. For example, the largest source of these neutrinos are something called as supernova, and we'll discuss about supernova a little later. So neutrinos make up 0.3% of this entire universe. Then 0.17% are antimatter and electromagnetic radiation. Antimatter and electromagnetic radiation. Now, about electromagnetic radiations, we'll discuss later when we go to the chapter of IT and communication. We'll discuss about this electromagnetic radiation. Antimatter. What do we mean by antimatter? We discussed about antimatter and antiparticles in yesterday's class also. So, when we say that something is antimatter, the meaning of antimatter is the particles or matter with same mass but opposite charge. Same mass but opposite charge, then in that case we'll say that these are antimatter. So for example, let's say when we have electrons and protons, can we say that electrons and protons are antimatter of each other? Can we say that, pick A for yes and B for no? Do you think that these two can be called as antimatter of each other? Electrons and protons, can they be called as antimatter of each other? Hmm, interesting. 65% of you have said yes. It cannot be yes. Why? Because we are saying that they need to have same mass. Protons and electrons, they do not have same mass. Protons are almost 2000 times heavier than electrons. So that's why here the correct answer will be no. These are not antimatter. If you remember yesterday, we discussed about positrons, right? We discussed about positrons. So electrons and positrons, they are antimatter of each other. They are antimatter of each other because positrons and electrons, they have opposite charge and they have the same mass. Whereas in case of protons, the masses are not the same. Protons are way too heavy as compared to an electron. So that's why they are not comparable in their masses. They are very, very different in their masses. So that's why just remember this, that when we say that something is an antimatter, the meaning of antimatter is that you have same mass but opposite charge. And then lastly, we have the 0.03%. And this 0.03%, we are saying that these are heavy elements. 0.03% are heavy elements. Now, when we say heavy elements, the meaning of heavy elements, basically, heavy elements are all the elements apart from hydrogen and helium. Apart from hydrogen and helium, every other element, they are called as heavy elements. So every element apart from hydrogen and helium. Every element apart from hydrogen and helium, they can be called as heavy elements. So that's why when it comes to heavy elements, they make up just 0.03% of this entire universe. Just 0.03%. So basically, everything that you look around and everything that you find around you, they are made of heavy elements. Correct? So that makes up just 0.03% of this entire universe. So that's why even out of this rest of the universe also, which makes up 5%, if you think of what we can actually see, is a very, very tiny fraction of it. Correct? So that's why majority of the universe for us still remains unexplored. And talking about unexplored, this is where we come to dark energy and dark matter. And dark energy and dark matter, we are saying that they make up 95% of this universe. So what do we mean by dark energy and what do we mean by dark matter? Let's try to understand this. That first dark energy and then dark matter. That what is dark energy and what is dark matter. Now, when it comes to dark energy or dark matter for that matter, uh, when we say dark, it does not mean that it has some negative sense or negative connotation with it. There are some dark forces, dark energy and dark matter. No. Why we say dark energy is mainly because we are in the dark. We do not know what kind of energy it is. We just know that there is some form of energy that exists, but we do not know what form of energy it is. We do not understand what kind of energy it is, and hence we have called it as dark energy. All right, because we do not know, we have no idea what kind of energy it is. We have been trying to understand what this energy is, but we still don't know. But if we don't know, how do we know that it exists? If we do not know what form it is or what kind of energy it is, then how do we know of its existence? How do we even know that something like this even exists? The reason is when we understand this entire universe and the structure of the universe. Now, here I'll go a bit into the history of our understanding of the universe. Initially, we used to believe that this entire universe is in a static state. All right, it is in a steady state. Now, meaning of steady or static state is that we used to believe that the universe is always like this. The universe always has been like this and it will always be like this. So there is no change that ever happens in the shape or the structure of the universe. So this is something that was also called as the steady state theory, where we used to believe. So steady state theory, it was called as steady state theory. So the steady state theory basically was saying that the shape and structure of the universe, shape and structure of the universe always has and will remain the same. All right. So the relative structures or the relative positions of all the parts of the entire universe will not change. This is what was called as steady state theory. And it was very strongly believed that this is correct. But then came Albert Einstein. And then Albert Einstein, when he was working on his theory of relativity, this is where he found that the universe should be expanding. According to his calculations had shown that the universe must be expanding. But even he was a strong believer of steady state theory. So he thought that he had made some mistake. He thought that he had made a mistake in his equations, in his conclusions. So then he changed it. It's like when you know the answer, right? When you know that, okay, the answer has to be 5. So you'll make sure that the answer comes out to be 5. You'll write all the steps in the mathematical calculation so that you get the answer as 5. So something similar happened with Albert Einstein also, that because he believed that steady state theory is correct, even though his calculations were showing something different, he still changed his calculations. He changed his equations in a manner that the universe becomes steady again. So Albert Einstein did this. But then after that, we see comes another scientist by the name Edwin Hubble. Now, what does Edwin Hubble say? Edwin Hubble, again, independently, with his independent set of theories and calculations, proved that the universe is indeed expanding. All right. So Edwin Hubble, he proved that universe is expanding. Albert Einstein also read this. He read the theory that was given by Edwin Hubble. And then Albert Einstein said that this was the biggest blunder of my life. That this is the biggest blunder of my life, because it could have been in the name of Albert Einstein. He could have gotten the theory in his name, but unfortunately, because he did not believe that he was right, he changed the equations. So when Albert Einstein did not believe in himself, forget about people like me and you. Even he did not believe that he was right. He had self doubt, and this self-doubt led to him changing the entire equations, and ultimately it went to Edwin Hubble. And Edwin Hubble proved it independently almost 12 years later that the universe indeed is expanding. Now we found that fine that he proved it that universe is expanding. Now one thing is fine that okay, here we found that the universe is not only expanding, but rather it is expanding in an accelerated manner. What do we mean? A normal expansion would have mean something like this. A normal expansion. Accelerated expansion means that it is expanding like this. So this is normal expansion, and this is accelerated expansion. So initially he just had proved that okay, universe is expanding, but later it was found that it's not only expanding but expanding in an accelerated manner, something like this. As you can see that it is expanding like this, the universe is expanding like this, that if you see the relative positions between the galaxies are like this is moving further apart and this is moving further apart, meaning that the expansion is happening everywhere in this universe. All right, this accelerated expansion is happening everywhere in the universe, and that's why all these galaxies, they are basically moving apart. They're moving apart. It's just like, let's say if you have a balloon and you mark a couple of points on the balloon, and then you start inflating the balloon, what will happen? That these points will start moving apart, correct? So something similar is happening here, that the universe is moving apart, or this entire all the galaxies etc, they are moving away from one another. So universe is expanding in an accelerated manner, and this was proved later that there is an accelerated expansion that this universe has. Now for this accelerated expansion to happen, there must be some energy behind it. For any kind of work to be done, you need energy, right? If you have energy, then only some kind of work can be done, and that's true for anything or any kind of work that happens. So similarly here also, if this expansion is happening, there must be some form of energy that is running the show, that is behind this accelerated expansion. Now what kind of energy it is, we don't know. We still are confused about it. We still do not understand what form of energy it is, but we do understand that there must be some form of energy that is leading to accelerated expansion of the universe, and this has been called as dark energy. So that's why, in simple terms, dark energy is an unknown form of energy which is hypothesized to permeate all of space, tending to accelerate the expansion of the universe. So that's why the energy behind the accelerated expansion of the universe is called as dark energy. Simple. All right. What is dark energy? In just one line. Forget about all the stories that I told you. Just one line about what is dark energy. The energy leading to accelerated expansion of the universe. The energy leading to accelerated expansion of the universe is called as dark energy. That's it. That's the only line that you need to know about what dark energy is. Now coming to the second concept, and this is the concept of dark matter. That what do we mean by dark matter? Now in dark matter also, let's say I give you a scenario so that you understand what dark matter is. Suppose that you are studying in your room uh, at very late in the night, and while you are studying in your room, I ask you to weigh this room and everything that is there in the room. So let's say you start finding the mass of each and everything that you are there, your maybe bed, your maybe study table, your books, your clothes, all these things, plus let's say all the bricks and walls etc. You keep measuring all that, and you find that overall, individually, when we you weigh everything, it comes out to be 1000 kg. But then I ask you to weigh the entire room, that pick up the entire room at once and weigh it. And when you weigh that room, you find that it's not 1000 kg but maybe 2000 kg, or maybe 1500 kg, let's say. Now you have already taken into account everything, even the air that you have in this room. So then how is this extra mass coming from? So there are possibilities that there is something else in the room also that you cannot see, you cannot observe, but it exists, correct? So and that is why the weight of the room is increasing overall. So if this is the scenario in your room, that let's say when you are studying and when you are watching a lecture, you are not the only one watching the lecture, but there are others who are also learning. and others who are invisible, but they are also learning. So then this is the case of dark matter. And this entirely, when you look at the universe, this is actually something that happens in the universe also. That in the universe, apart from whatever we have observed, our calculations show something else. Our observations have shown us a lot of celestial bodies and everything that is visible through our telescopes and all the instruments and machinery that we have. But apart from that, when we do the calculations for, let's say, any given galaxy, let's suppose that we are watching a galaxy, and while watching the galaxy we have seen that, okay, these are all the planets and all the celestial bodies, stars, etc., that are there in the that galaxy. And whatever we have seen and everything that we can see and all the things that we can observe, we have done a mathematical observation, and hence we understand that, okay, fine, let's say 1 lakh kg is the mass of that galaxy. But when we do the calculations based on the movements and the gravitation and all these things, then we find that the calculations show that the mass should be way more than that. So why way more than that, we do not know. It simply means that there must be something else. There must be something else which is not visible, but it does have mass. So that has been called as dark matter, the unknown matter, the matter that must exist in this universe, but we are not able to observe it. Our current instruments cannot observe it. So that's why this kind of matter has been called as dark matter. So matter that exists but is not visible, simple. All right, the matter that exists but is not visible. So that's why it makes a vast majority of matter in the universe, but it is mysterious, non-luminous, and uh, uh, it becomes impossible. Dark matter is impossible to detect with the current instruments. So in simple terms, what you can say is that this is matter that exists in the universe, but is currently not observable. So this kind of matter is called as dark matter. So that's why we have these two concepts. One is of dark energy. Dark energy is the kind of energy that leads to accelerated expansion of the universe. And then you have dark matter, which basically is the matter that exists but is not visible. So that's why dark matter. So dark energy and dark matter, they make up almost 95% of this entire universe. Now, there are various efforts to understand what dark energy and dark matter is. One of the most recent and probably very important for this year's prelims examination will be Euclid mission. Now, Euclid mission, basically, the basic objective of the Euclid mission is to explore the dark universe. Now, when we say the dark universe, the meaning of dark universe is dark energy and dark matter. All right, so this is a mission to explore dark energy and dark matter. So that's why just remember Euclid mission. And we see that these kind of news articles keep on coming, that it has captured unprecedented views of deep space, and there are new observations, and all these things will keep coming from time to time. So Euclid mission, from the examination perspective this year, can be a very, very important mission, because it is out there to try and observe dark energy and dark matter. So, any questions from whatever we have discussed until now with regards to dark energy and dark matter, especially? Anything that you want to ask? If energy cannot be created nor destroyed, how the initial energy came? So, now this is where the problem lies, that all the when we talk about the universe and the formation and the existence of everything in this universe, we just say that it already has existed forever. Even the Big Bang theory, which tries to make us understand the formation of this universe and how the universe came into being, even it does not talk about how exactly it comes into being. It talks about after it already started existing. So that is something that has been one of the most problematic and unexplained things in science, that Even if we are saying that it cannot be, new energy cannot be created nor destroyed, then where did this energy or the first energy come from? Non-luminous simply means that this basically does not respond to light or does not respond to electromagnetic radiation, so it cannot be observed. So non-luminous means that it is not, does not have a source of light, or does not, is not visible with light, that even if you are looking with a torch you cannot see it. So then in that case it will be called as non-luminous. But not only light, but rather every electromagnetic radiation. Dark energy slide once. Dark energy slide. Hmm. Which country is involved in the Euclid mission? It's largely European Space Agency and NASA. Biggest explosion humans have seen, which is luminous explosion of stars. Yes, you can say that. Where can I get the information related to Euclid mission? You can directly, I mean, even if you do a simple Google search, you will find it. It's a very important and a very popular mission right now. It was just launched last year only. Earth is in a vacuum. Our scientists are sending rockets and satellites through gravity. But sir, no one is going to the space below the Earth. There is nothing below called as below the Earth. So basically, when we are saying the Earth basically is a sphere, so you cannot say that something is above and something is below. Everything is basically, when you look up, you are basically looking at one side of the Earth. So you exist at some point of the Earth. So it's not that there is something which is below. Earth lies in this vacuum where you have uh, basically, you can say that this entire universe has a kind of a two-dimensional structure to it, and then we are launching something which is omnidirectional. So there is nothing which you can say is above or below in that sense. Why heavy elements are not parts of stars? The stars basically are made of hydrogen and helium, so they do not really have all these elements. Do anything that the Euclid telescope finds not related to called as dark matter, dark energy? Not until now, nothing as such, but we hope for the future. Non-luminous simply means that there is something. Uh, Non-luminous simply means that there is something called, let's say, something that cannot be observed with the help of uh, the electromagnetic radiations, any kind of electromagnetic radiations for that matter. Please explain dark matter once again. So dark matter, just remember this in very simple things, that it's matter that you can't see. All right. It's just like a ghost, that even if the ghost is sitting right beside you, you cannot see it. Similarly, it's kind of matter that we are not able to observe with all the telescopes and all the instruments that we have. We are not able to see it. We are not able to observe it. But it must exist because it is what is adding to the entire mass of the universe. So that's why mass exists, so it means that matter should exist, but we haven't been able to observe it. Who is also with you in the studio is dark matter? I hope not. Our body weight also is dark matter. We can't say that. I mean, dark matter is individually matter that will occupy space and will have its own mass. Is black hole dark energy or dark matter? None of the above. We'll discuss about what black holes are. Our solar system, which is situated in the Milky Way, how the sun is moving in it. The sun basically moves as a system. As the entire system moves, it moves as a system in maintaining the angular momentum of this entire solar system. How would we know about dark matter existence? It's just calculations. It's simply calculations that we have carried on, which led us to believe that they exist. We want to know about the mass of dark matter. We It's very difficult to understand the entire thing, but we believe that almost 85% of all the matter that exists should be dark matter. Sun is moving along the Milky Way. Yes, as an arm of the Milky Way, it is moving along with it. Hmm. So next up is formation of the universe. Now, when it comes to the formation of the universe, there are various different theories that we have with regards to the formation, and this is where most important and the most widely accepted theory is the Big Bang theory. Apart from that, we discussed about steady state theory, that how now we have more or less believe that we now know that steady state theory cannot be correct. Then there is eternal inflation theory that talks about the concept of multiverse, that there is not one universe but there are multiple universes that exist, but again there is very little scientific evidence to prove that there are multiple universes. Then after that you have oscillating universe theory, which says that the universe right now is expanding, but it keeps on expanding and contracting. So it says that universe expands and contracts. And even the big bounce theory says something very similar, that it contracts and expands, but again very little scientific evidence to prove these. Then there is string theory, and we'll discuss about string theory in detail because that's a very very important theory for us. Now, overall, the most widely accepted theory right now is the Big Bang theory. So, what is Big Bang theory? Let's try to understand. Others are not really important and they cannot be asked in the examination. Two are important. One is the Big Bang theory, which is important, and the other one is the string theory. So, we'll discuss these two in detail because they are very often in the news, and in the context of science, they are the ones where the most wide discussions happen. So, that's why these two. So, first is the Big Bang theory. Now, what the Big Bang theory says is that the universe was very hot and concentrated in the distant past, and ever since then, it has been stretching and cooling. So, what it says is that the entire universe, when it began, it was just a very small point. It was just a very small point, very small particle rather, and a particle which would have been even smaller than the size of a proton. So, meaning that the entire universe was smaller than a proton, according to this theory. And at this point of time, very hot. The temperature could have been of the order of 10 to the power of 32 degrees Celsius. So 10 to the power of 32 degrees Celsius would have been the temperature of the universe, and this entire universe would have been just like a soup. That how in a soup you have various ingredients just mixed. Similarly, in this universe also, all the different types of forces, matter, energy, etc., they would just have been mixed like a soup in this very, very, very small particle, smaller than the size of a proton. And then suddenly expansion starts. All of a sudden, because of some kind of trigger, it starts to expand. And as it starts to expand, this is where all the matter, energy, etc., they start uh, existing independently. All right, they all start existing independently for the first time. So this is what the Big Bang theory says, uh, and since then it has been stretching and cooling. Now, the Big Bang Theory has been able to explain a lot of things that we had predicted, that we thought would be true. We see that the Big Bang Theory has been able to explain all that. And that's why Big Bang Theory becomes very, very crucial in that regard, because everything that it has predicted, everything that it has said came out to be true later. And that's why there are certain evidences that become very crucial uh, in the understanding of the Big Bang Theory. So, three major evidences that support the Big Bang Theory. First, called as Hubble expansion. Hubble expansion is nothing but the accelerated expansion of the universe. So the accelerated expansion of the universe is called as Hubble expansion. So we have now been able to find this to be true, that the universe is expanding in an accelerated manner. Now the important thing is that the Big Bang Theory had predicted accelerated expansion in the 1960s, and in 1990s we found it to be true, that we were able to find the evidence that the Big Bang, that the universe is expanding in an accelerated manner. So that further solidified the Big Bang Theory. So that's why Hubble expansion has been very, very crucial. Similarly, there is Big Bang nucleosynthesis. Now, Big Bang nucleosynthesis is nothing but the abundance, the abundance of hydrogen and helium. So the abundance of hydrogen and helium is Big Bang nucleosynthesis. That's it. So that's a although very fancy term, but the meaning is simple. And we discussed that almost 4% of the observable universe is just hydrogen and helium. So out of the 5% that we know of, 4% is just hydrogen and helium. And that also is something that the Big Bang Theory had predicted that it must be so. And then later we found it to be correct. And then lastly, cosmic microwave background. What do we mean by cosmic microwave background? Now, when we say cosmic, what is the meaning of cosmic? That it is something related to the space. So something related to space is called as cosmic, something related to the universe. Microwave, what is microwave? Microwave basically is a type of electromagnetic radiation. We'll discuss about microwaves later also in another chapter. But microwaves, for now, just remember that it's a kind of electromagnetic radiation associated with heat. All right. Electromagnetic radiation associated with heat. All right. So electromagnetic radiation associated with heat. And background because it is visible in the background, something like this. If you see this, that if we, let's say, are observing the universe through our instruments from sitting from on the earth, and let's say we are looking at the outer space. Now as we are looking at the outer space, we see all the celestial bodies like stars, planets, etc. All these are visible, and in the background, as you can see here, in the background, microwaves are visible. And the visibility of these microwaves, they basically tell us about a fact that the universe, when it began, must have been very hot and concentrated, and that's why the heat remains of the early universe is seen as these microwaves. So these microwaves basically mean this. So this basically is cosmic microwave background, and they signify presence of enormous amount of heat in the early universe. So this is basically what cosmic microwave background signifies. So cosmic microwave background first was seen with the help of a mission called as COBE in 1993, and for the observation of these cosmic microwave background, a Nobel Prize was also given to this mission. Then there was this second mission called as WMAP, which was taken in 2006. It gave us a clearer picture of the cosmic microwave background. And then after that, there is the third mission called as Planck, which was taken in 2009, which gave us even better and more detailed picture of the cosmic microwave background. And that's why this is what it signifies. As you can see here, that we are trying to showcase WMAP, right? So WMAP basically is WMAP basically is being shown here in this picture also, and that signifies how it has been able to observe cosmic microwave background as one of the most important evidences of what Big Bang theory has said. So Big Bang theory said that the universe is very hot and concentrated in the distant past, temperature being 10 to the power of 32 degrees Celsius, and ever since then it has been stretching and cooling. So that was said in 1960s, and in 1993 for the first time we observed it with the help of this particular space mission. So then it further solidified. That's why these evidences, they further solidified the Big Bang theory, and that's why Big Bang theory became the most widely accepted theory altogether. So now one thing to remember, what we are saying, that there was an expansion that started in the universe. All right, it talks about an expansion that started in the universe, and always remember that it was an expansion, because in many of the sources what I see is that they say that an explosion happened in this particle, that this small particle there was an explosion. But saying that it was an explosion will be technically wrong. So please ensure that when you write, you always say that it was an expansion. There was an expansion that started in the universe, and it was not an explosion that happened in the universe. So please remember this, because unfortunately in many of the sources, even if you go to the internet, you'll find that in many of the sources they would write that an explosion happened, but not explosion, expansion. So please remember this, because on the internet you have a lot of wrong information available here with regards to the Big Bang, especially this, the beginning, that it was an expansion. Now the next one is string theory, but let's take a break here, and on the other side let's come back and start discussing about the string theory and what a string theory is. So it's 6:38 right now. Can we be back by 6:50? Six, okay, 6:55 is still. I'll take your questions first anyway when I come back, and then after that let's say we'll begin in another 3-4 minutes after that, but not 7. 7 is, you're saying that we should take 20-25 minutes break. Welcome back, everyone. So, next topic for us is string theory. Any questions if you have from Big Bang Theory? Is UPSC syllabus used for any other competitive exam? No, no. Although GS syllabus, you can say, remains the same more or less, but the kinds of questions are very, very different. The way UPSC asks question in your prelims and mains is pretty different from everything else. I'm a fresher. Your number, I mean, it's very difficult for me to share my number and commit to picking the calls, but I would still give you my email ID. And if you have anything that you want to ask me, this is the email ID. You can contact me here. Because given my schedule, it's almost impossible for me to pick up the calls with the classes and everything. So it's better that you contact me on email instead. Does cat help CSAT? See, again, what happens here is that cat would ask questions which are pretty different in this scenario, and although it remains the same in a manner that uh, the same numeracy is being asked or same arithmetic is asked and all those concepts are similar, but the level of difficulty in cat will be pretty high compared to csat. So that's why the cat preparation might in one way help in csat, um, partially. But what happens in the difference is that in cat you are given a lot of time to solve questions because questions are of difficult level. So that's why you are given more time to solve the questions. But in your UPSC, in your CSAT paper, the amount of time that you get is less because the number of questions are more. So what happens is, as you prepare for cat, the way you approach cat is a bit different in that sense, because you know that you have that time to solve very difficult questions, whereas here you will have to use more of shortcuts and maybe also memory at times to solve these questions. So that is where it's different. What is meant by the accretion theory of earth? So accretion theory of the earth basically says that everything started from dust and gases, and all these things started to small clumps of gases would have started forming, and then from there on the formation of the earth would have happened. So this is basically what it says. It talks about the concept of planetesimals, for example, that there are small planetesimals which were formed, that is basically minor planets, small planets, and they basically their clusters they led to the formation of a planet. How universe is expanding from small mass, like you told in Big Bang. Is it matter coming from dark matter also? Not really. The expansion happened mainly because there was a lot of pressure building up from inside. This is one of the theories, and that led to this expansion. And while this expansion happened, all the newer matter were also being formed. And while this newer matter was formed, new kind of particles and new kinds of energy, etc., they started coming in into formation. Right. So let's move to the next topic, and the next topic is string theory. Now, when it comes to string theory, it has been, you can say, after the Big Bang, if there is some theory which is very widely discussed, it is the string theory. Now, what does string theory say? String. It talks about strings, and it says that the entire universe and every particle, every kind of matter, and every kind of force, all these are made of tiny strings. All these are made of tiny strings. Now, what it basically says is that the entire every matter, whether it is a particle, I mean it is a mass matter or a force particle, matter particle or force particle, all these particles basically are made of very tiny strings, and vibrations in these tiny strings will produce different types of matter. So whether a proton will be produced, or an electron will be produced, or a neutron will be produced, or a gravity force particle will be produced, or an electromagnetic particle will be produced, it all depends on what kind of vibrations happen in this particle. So these strings rather. So everything is made of very tiny strings, and these tiny strings will ultimately make up matter, is what string theory says. So describes the fundamental level of the universe in terms of vibrating strings rather than particles. So that is exactly what it says, that all matter and force are made of very tiny strings, different vibrations in these strings lead to the formation of various particles, right? So all the particles, everything that we know of, everything are formed from these tiny strings according to string theory. Now in this string theory, one thing which is very very important about string theory is that the string theory says, string theory becomes a candidate for theory of everything. Now this theory of everything also has been a very important theory and a very widely discussed theory in the last 2 3 decades at least. Now, what does this theory of everything say? Because it is saying that it is considered as a candidate for theory of everything, as it tries to explain the four fundamental forces. Now, let's try to understand these two things. What do we mean by these fundamental forces, and what is this theory of everything? So, four fundamental forces. Do you know which are the four fundamental forces? Which forces are called as the fundamental forces? Can you name them? Yes, gravitational force, correct. Strong and weak nuclear forces, correct. Electromagnetic force, perfect. So you have the strong nuclear force, strong nuclear force. Then we have the weak nuclear force. Then we have the gravitational force, and then we also have the electromagnetic force. So these four forces together, they are called as the fundamental forces. Let me just switch their sequence here. Electromagnetic force, and gravitational force. Right, so these four are called as fundamental forces. Now why they are called as four fundamental forces? Because they are related to four completely different aspects of existence. So basically, strong nuclear force is very different from weak nuclear force, that is very different from electromagnetic force, and that is very different from gravitational force. And all these are not interconvertible. There is no relation, there is no one equation to rule them all these are very different, all these are differently seen, and we are not able to find a relation where all these four forces can be seen together. That if there was just one equation to rule all these four forces, we haven't been able to do that. And when we do that, that is called as theory of everything. All right, so theory of everything basically is study of all four fundamental forces together in a single theory. So that is called as theory of everything. Now in this regard also, when it comes to these four fundamental forces, also know the magnitude of their strength. Strong nuclear force is the strongest of all these forces. Then after that you have the electromagnetic force, then that is followed by the weak nuclear force, and compared to them, gravitational force is the weakest force. All right, gravitational force is the weakest of all these four fundamental forces, and that's why these three forces together, they are also called as the standard model. They many a times are also called as the standard model of physics. Now why we call it as a standard model of physics is largely mainly because of the fact that when it comes to the three forces, these are the three forces which are very strong, and they have somewhat similar behavior in observation, and that's why they are said to be the standard model. And gravitational force compared to all these three forces is a very very weak force, and that's why in the standard model we are not using gravitational force. So this is basically how we look at these fundamental forces. Now, and why string theory? That's why this string theory becomes important, because if string theory comes out to be correct, the problem is that these, when we say very tiny strings, these tiny strings simply mean that these are so tiny that they are not observable. Currently we do not have anything that can observe these particles or these strings, the so-called strings. So unfortunately right now it still just remains a theory with no proof whatsoever, and we cannot find a proof uh, to find a relation here, to understand whether it can happen, not happen, or all that. Mainly because when it comes to uh, these tiny strings, these are so small. We talk about the order of 10 to the power of minus 35 meters. There is no microscope that can uh, see something up to 10 to the power of minus 35 meters. So that is all what actually leads to this string theory being a theory which does not really have a lot of proofs. But if proved to be correct, physics as we know will change. Everything that you are being taught will change. So a lot of things will be very different in the manner that how we look at things. Read this question. This was asked in your 2017 prelims paper. A very simple question. I'm launching the poll for you. Wonderful. So 82% of you have marked A, which is the correct answer. The terms event horizon, singularity, string theory, and standard model sometimes seen in the news in the context of first, observation and understanding of the universe looks to be correct. Second is study of the solar and lunar eclipses. We did not discuss anything about the eclipses. Placing satellites in the orbit, not related to it. Origin and evolution of living organisms on the earth. So it's not only about the living organisms and not only about the earth. We have not yet discussed event horizon and singularity. We'll discuss that later. But we discussed about string theory, we discussed about the standard model, and both are related to the observation of the universe and understanding of the universe. So that's why the correct answer here will be A. Now coming to the celestial bodies. So now we have an understanding of what the universe is, how the composition is like, and some of the things related to that composition. Now when it comes to the understanding of a star, the most important celestial body, because it occupies such a huge space and huge amount of mass of this entire universe, It is a celestial body that generates light by nuclear fusion reactions and is held by its own gravity. All right. So two important criteria, I would say: one, nuclear fusion, and second, held by its own gravity. In a manner, you can say that it has a spherical shape. It has kind of a spherical shape due to gravity, because gravity acts on all the sides simultaneously and it gives it almost kind of a spherical shape. So that's why nuclear fusion and gravity, these two become the most important, most crucial points with regards to the understanding of a celestial body like a star. So this is how we define a star. Now when it comes to the formation of a star begins with a nebula. Now, these pictures that you see right here, this is a nebula. And if you know about a nebula, what is a nebula? Nebula is the most common screensaver and wallpaper of the world. Uh, and there is a research that was conducted a few years back with regards to which one thing is used mostly as a screensaver or a wallpaper on mobile phones and laptops and computers. It came out to be nebula. So look very beautiful, right? Nebula look very beautiful. What exactly are nebula? Nebula, basically you can say that these are clouds of dust and gases. These are clouds of, or a region of dust and gases in the universe, and this is where the formation of a star begins from. So this is region of dust and gases, also called as star nurseries, because generally stars basically will be formed from nebula, and that's why they are also called as star nurseries. And these are nothing but just region of dust and gases, hydrogen gas, helium, other ionized gases, dust particles, all these will be just arranged somehow, sometimes in a regular shape, sometimes in a irregular shape, but they will look very beautiful, very elegant. And if you just go and do a Google image search of nebula, you'll find wonderful images, and you'll also be tempted to use it as a screensaver or a wallpaper. So that's why nebula. And so the stars, they originate from a nebula, and gravity then pulls together all the dust and gases from the nebula to form a very small size star, which is called as a protostar. And this is where we see that now, after the formation of a protostar, there will be some time where, because of gravity, because of this ball of mass that is being created, it will start pulling everything else towards it. And this is where a small ball of mass is formed and hydrogen starts to react. Nuclear fusion starts here. The conditions are such that nuclear fusion starts, and ultimately it leads to the formation of the core of a star. So the star formation basically begins from here. So ultimately, we see that it starts to become bigger ball of mass, and ultimately, from this protostar, the formation of the star happens. Now, when it comes to the formation of a star, one thing that is very important for us to also understand is about the life cycle of a star. Now, star starts from a nebula, as we just discussed. From here, the formation of two types of star can happen. Either an average star or a massive star will be formed. Either an average star or a massive star will be formed. Now, let me ask you a question. When our sun dies, it will convert into a black hole. A yes or B no. Please tell me what you think the answer is. When our sun dies, it will convert into a black hole. Will it convert into a black hole, or it wouldn't convert into a black hole? Hmm. So 51% of you feel it will not, and 49% of you feel that it will. The answer is no. It will not convert into a black hole. This is one of the misconceptions. We have heard, or you might have heard, that black holes are formed when star dies. Correct? But it's not that if every star dies, or with when any star dies, it will convert into a black hole. That's not right. Only the massive stars, only when a massive star dies it will convert into a black hole. Otherwise it will not convert into a black hole. An average star, when it is about to die, it first converts into a red giant. All right, red giant. So red color signifies low temperature, giant meaning very huge size. So it will be converted into a bigger sized ball of mass, bigger sized star with very low surface temperature, and then it ultimately converts into a nebula, a planetary nebula. Now planetary nebula is nothing, has nothing to do with planets. It's not that it leads to the formation of a planet or has been formed because of a planet. No. Just because of the kind of shape that it has been given the name planetary nebula, and because of the fact that scientists like uh, to confuse people, and that's why unfortunately the name is planetary nebula. Otherwise, it has nothing to do with a planet. So a nebula will be formed, and ultimately, it forms a white dwarf. An average star forms a white dwarf. Now, our sun is an average star. How do we define an average star? Every star every star with mass up to 1.44 times mass of the earth, sorry, mass of the sun. So every star with mass up to 1.44 times the mass of the sun are called as average stars. All right, these are all called as average stars. So our sun also is an average star. All right, our sun also is an average star. So what we mean is that if you consider sun to be 100 grams, then every star with up mass up to 144 grams will be called as an average star, and above that you will have massive stars. So above that you have massive stars. So when massive stars are dying, then they are first converted into a red supergiant, and then after that, in this red supergiant, supernova happens. Now this supernova basically is an explosion. This is an explosion at the core of a red supergiant. Right, explosion at the core of a red supergiant is called as a supernova. So this supernova basically is a huge explosion that happens because now red supergiant starts to become very unstable. As it is about to die, it becomes very unstable, and as it becomes unstable, this is where explosion happens at the center, and this explosion is called as supernova. And if you remember, we had discussed that supernova are the largest source of neutrinos in this universe. So largest source of neutrinos in the universe. So supernova. After supernova, there are two possibilities. One, that a neutron star can be formed. So neutron star, basically these are the smallest stars. These are the smallest stars of the universe. So either a neutron star will be formed, or if not, then in that case black holes will be formed. So either black holes will be formed or neutron stars will be formed. So even in case of massive stars, there is no guarantee. All right, even in case of massive stars, there is no guarantee that when the massive star dies, it will convert into a black hole. It can, it may convert into a black hole. It doesn't always convert into a black hole. All right. So that is how we understand that. where black hole formation happens. So that's why sun will never form a black hole. Any average star will never form a black hole. Only massive stars will be forming black holes, otherwise not. All right. And and even in case of massive stars, they might form black holes. It depends on the mass of the star, mass of the massive star. If the mass of the massive star is up to 2 times or 2.2 to 2.3 times the mass of the sun, then in that case chances are higher that it will form a neutron star. And when it is above 5 times or above 6 times the mass of the sun, then in that case chances are higher that it will form a black hole. Now, even from here, there is a one question that has been asked. Just read this question. So already some of you have given the answer before the question was asked. Good. Hmm. Who among the following scientists proved that stars with mass less than 1.44 times the mass of the sun end up as white dwarfs when they die? This was given by an Indian scientist, S. Chandrasekhar, and that's why this number 1.44 is also called as, if you have heard of it, Chandrasekhar limit. This number is called as Chandrasekhar limit. It was named after him because he was the one who proved it, that if the masses are up to 1.44 times, then only white dwarfs can form, and then neutron stars or black holes cannot form. So that's why it was named in his honor. It was named as this number 1.44 was named as Chandrasekhar limit. Now, coming to the concept of black holes, what we discussed is that when massive stars die, they might form a black hole. Now, what do we mean by black holes? And these have been one of the most intriguing concepts that we know of. And the significance of this picture right here is that this is the first picture that we have taken ever of a black hole. If you look at the other pictures, if you do a Google search, you'll find very elegant, very beautiful pictures of black holes. So that was our impression of how the black hole would look like, that these kind of images would surface, that okay, this is how black holes might look like, and these might be the pictures and of the black hole. But then finally we found the black hole, or we were able to take a picture of a black hole. So this was the first picture taken or ever taken of a black hole, and these are, you can say, artist's impression of how the black holes might look like. So now this picture of a black hole that was taken, this also has been very significant in our understanding of black holes. That what we understand here is that when it comes to a black hole, there are two terms: black hole. First term is black. Why black? Because of absence of light. Because this is an area which is signified by absence of light. So black because of absence of light. Black because of absence of light. And then the second term is hole. Why the term hole is being used? Because in a manner you can say that it is like a well. That, for example, if you consider any well, a well might have a boundary, right? A well might have a boundary. And if someone crosses this boundary, what happens then? You fall. Don't try this at home. If you've crossed that boundary, what happens? The gravity will pull you towards the center of this well, and you'll fall towards the center of this well. So that's why black hole, because very similar something happens for a black hole, that there is, you can say, a kind of a boundary. And if any particle crosses this boundary, then it simply goes towards the center. It will simply go and go towards the center of this black hole. So that's why these two points become very, very crucial. One, the boundary of this black hole, and secondly, the center of the black hole. So if you look at this figure, you have this boundary of the black hole. So this boundary of the black hole, this is called as event horizon, right? This boundary of the black hole is called as event horizon. So this boundary is called as event horizon. And the center of the black hole, the center of the black hole is called as singularity. Center of the black hole is called as singularity. So let me define these for you. So event horizon, basically the boundary beyond which if a particle goes, then it falls towards the center of the black hole. When it falls towards the center of the black hole. And then we have the concept of singularity. So concept of singularity says that this is nothing but the center of the black hole. Center of the black hole is called as singularity. So until now we know about these black holes, and we understand that these black holes are spaces or places in space where the pulling force of gravity is so strong that even light cannot escape. That even light cannot escape this black hole because pulling force is so strong, and that's why it is black. That's why we say absence of light, because when light even when if you look at even this figure, when light crosses even this event horizon, it will just fall into the center, and that's why it will be invisible, and that's why this entire center is invisible, because even the light particles are not able to escape this black hole. They fall towards the center of this black hole. The light particles, the photons as we call them, they fall towards the center of this black hole. So now in this particular scenario, when it comes to the black hole, this was a picture that we were able to take of a black hole with the help of telescopes which are called as Event Horizon Telescope Program. Event Horizon Telescope Program. Now, this Event Horizon Telescope Program is a program with regard to finding of a black hole. So we were able to take the picture of a black hole with the help of Event Horizon Telescope Program, which actually is not a single telescope, but rather a set of telescopes which have been located at the different parts of Europe and North America, South America, etc. So a set of all these telescopes working together into taking a picture of a black hole, and we succeeded in 2019 when we took the picture of M87 black hole, and that's why it was the first picture that we ever took of a black hole. And then after that, there is another black hole that we have at the center of our Milky Way galaxy as well, which is called as the Sagittarius A star, and we have taken in 2022. In 2022 we have taken the picture of Sagittarius A star, and this was the second picture that we have taken of a black hole. And Sagittarius A star as a black hole is it's very, very huge, it's massive, it's way bigger than M87 black hole, which is a normal sized black hole. Compared to that, Sagittarius A star is a very, very huge black hole that we have at the center of our Milky Way galaxy. Okay, this question I have for you. Asked for rupees 25 lakhs in KBC. Can you tell me what the answer is? Hmm. 78% of you have marked A, Rest 22% of you are not paying attention to the classroom. We just discussed about this, that this is a supermassive black hole that we have at the center of the Milky Way galaxy. And look at the prize money. That if you know the answer to this question, congratulations to the 78% of you. You have won rupees 25 lakhs. Unfortunately, I don't have that kind of money to give you. So, but this actually was a question for rupees 25 lakhs in KBC. So this Sagittarius A star has been very, very crucial, because it is a supermassive black hole that we have at the center of our own Milky Way galaxy. And for the first time, that's why it was a very exciting news that for the first time we have been able to take a real picture of the Sagittarius A star. Now, there is one concept which is very, very important, and this one concept is of gravitational waves. Now, again, gravitational wave is a concept which is related to the same discussions that we are having with regards to gravitational force. And this is something that was predicted by Albert Einstein back into 1915. And after 1915, it took us almost 100 years to prove that gravitational waves actually exist and detect one gravitational wave, for which even a Nobel Prize was given back in 2014. So gravitational waves. So that's why, that's the genius, and that's the uh, thing about Albert Einstein, that a lot of things that he had proved or had said, or had predicted in 1915s and 1920s and 1930s, they all came to be correct later. So that's why he figured out gravitational waves almost a century ago without having any access to any of the advanced technologies that we have today. So that's the genius of this man. So gravitational waves predicted by him. Now, what do we mean by gravitational waves? As the name tells you, gravitational waves, meaning that these are waves being formed because of gravitation, due to gravitation. That's why gravitational waves. Now, what do we mean by waves formed due to gravitation? Now, when we think of the space time, the entire universe that we have here, if you look at this figure, then the entire space time, wherever you have any celestial body, the celestial body makes a dent in this space time. Bigger the celestial body, heavier the celestial body, bigger will be the dent. Correct? So it's the entire space is thought to be like a mesh, like a net. Think of a football goal post. So if you have a football goalpost, what do you see? Every time somebody kicks a football into the net, what happens? Waves are generated. Correct? Waves are generated. The football makes a dent in it, and waves are generated. Something similar happens in case of this entire universe also. That if you have a celestial body makes a dent in that net. The heavier the celestial body, the bigger will be the dent. So, for example, let's say in the same football goal post, you take a very small stone and you throw that stone towards the football goal post. What happens? It perhaps doesn't make a dent, right? Even if it makes a dent, you do not even see that, you do not even observe it. It was so low, or it was so insignificant. Uh, but let's say instead of that, you take a football which is made of iron, all right, a football which is made of iron, and then you kick the football towards the football goalpost. What happens? First, you break your leg, and then when this football goes into the football goalpost, it will make waves which are very violent, right? It will make waves which are very violent. Something very similar happens in this universe, that wherever you have something which is very massive, you have very heavy, very energetic, they will make a dent which are going to make waves which are going to go very long way. So for example, black holes, merger of black holes, collision of black holes, collision of galaxies, merger of galaxies, supernova happening, all these kind of things, all these energetic events, very massive events, they will create a dent. They will create a dent where gravitational waves will be formed, and these gravitational waves will travel very long distances. Something like an earth, for example, cannot do that. Earth is like that small stone. In the context of this universe, earth is like a small stone, so it will not make a dent where gravitational waves will be very strong to be felt. But if, let's say, gravitational waves are being formed from something like all these, like collision of black holes, supernova, colliding neutron stars, etc. Even galaxies collide, galaxies merge, all these things, binary star system like this, a binary star system like this, all these kind of things can make us or can create gravitational waves. So this is what gravitational waves are, and these waves will be traveling at the speed of light, carrying the information about the origin and the nature of gravity. The first time that we detected a gravitational wave was with the help of this particular facility called as LIGO, Laser Interferometer Gravitational Wave Observatory, LIGO. So LIGO was where first gravitational wave has been detected. It's a observatory which is based in US, and this is where they were able to find evidences of gravitational wave, detected the first gravitational wave. And then after that we see that there are other developments also. For example, India is also developing Indigo LIGO, which was also in the news last year because Indigo LIGO, I've, sorry, I missed that newspaper clipping, I believe. But last year, the budget has been sanctioned for Indigo LIGO project. In 2016, we had announced that India is going to have its own gravitational wave observatory, which we are building in association with LIGO. So we are building it. We had announced it back in 2016, and last year the budget was also approved for the construction of the Indigo LIGO in that is an a gravitational wave observatory based in India. Then apart from that, there have been other observatories. For example, there is ELISA project, which is basically a space-based gravitational wave observatory. All right, space-based gravitational wave observatory. So that's why we say that these. So there have been all these efforts. Interestingly, from ELISA, UPSC has asked two questions in the prelims examination. One, I think, in 2016 and one in 2022. They've actually asked two questions from here, from this very small concept. So ELISA stands for Evolved Laser Interferometer Space Antenna. So same laser interferometer LI and space antenna. So this is a project where we are trying that we are setting up a gravitational wave observatory in space. Why space? Mainly because space is away from the Earth, away from the gravitational effects of the Earth, so makes it easier for us to detect a gravitational wave. Otherwise, in the presence of the Earth, it becomes very difficult to detect gravitational waves because Earth has its own gravitational wave, I mean gravitational force, and that will make it very difficult for us to detect a gravitational wave in the presence of Earth's gravitational field. So that's why this ELISA project. Read this question. 2019 they had asked this question. I'm launching the poll for you. Please mark your answers. Wonderful. So 83% of you have marked B, which is the correct answer. Recently, scientists observed the merger of giant black holes billions of light years away from the Earth. What is the significance of this observation? Right? So, merger of giant black holes. So, whenever merger of giant black holes happen, it's obviously a very massive event. So, if it's a massive event, black holes will be formed. So, correct answer, that's why will be gravitational waves were detected. Now here with D, it might be a confusion that you might think that, okay, we are talking about singularity and black holes have singularity, so maybe these two are connected. But we are talking about not just black holes, but merger of giant black holes. So without a doubt, gravitational waves will be created there, will be generated there, and this is exactly what happened. December 2018. December 2018, we had detected this gravitational wave, and that is what the question is based on. So that's why, although it's a current affairs question, but you don't need current affairs to answer this question. And we'll actually see a lot of these kind of questions here all across science as we discuss our modules, where although the current affairs question has been asked and it has some context in some kind of news, but many a times, if your concepts are clear, if your basics are clear, you do not really need that current affairs. Even without current affairs, you will be able to answer some of the current affairs question. And this is exactly the case in this scenario about this particular question. Now, next is about the sun. But before, again, if you have any doubts, if you want to ask anything from whatever we have discussed in last half an hour or so. Planetary nebula is also explosion. No, we cannot say that, because in case of planetary nebula, this is just a kind of nebula that is formed after, because I mean the core becomes unstable and starts to disintegrate. So it's more of a disintegration rather than explosion. What is angular momentum? Angular momentum basically is a momentum, basically something that you get because of the moment of inertia that we have in any rotating body or any circular motion. So it's just like how momentum is, where we are talking about mass and velocity, a product of mass and velocity. But here, instead of mass and velocity, we have moment of inertia and angular velocity, product of moment of inertia and angular velocity. But again, not required as a concept for explanation here. Can we see black holes in the night sky? No. Just imagine that how the scientists have struggled so much in making an instrument finally, that we in 2019 for the first time we could take a picture of the black hole. If we were able to see them, it would not be so difficult to make this entire program of event horizon telescope and then be able to take that picture. No, it's absolutely impossible. Our eyes cannot see, because our eyes see light and there is absence of light. Then how do you see something? You can't. Sun is big, stars are big. No, sun is an average size star. You cannot say that it's very big. Neither it is very small, nor it is very big. Can gravitational waves be detected even when there is no collision? Yes. I mean, anything that is energetic, anything that is massive, even just the presence of a massive black hole itself can create, or will rather generate, gravitational waves. When a man enters black hole, where would we go? It simply into at the towards the center of the black hole, will be pulled towards the center of the black hole and would disintegrate before reaching the center. What is nebula? As we discussed, it's just nothing but just a region where you have a lot of dust and gases, uh, may or may not have a specific shape, just that they exist in that region. And due to some ionization, it may so happen that nuclear fusion starts there and it starts to form a ball of mass, where then star formation might happen. How do black holes make light bend and trap light if light does not have mass? So see, Animesh, there are two things that you have to see understand here. One thing about the dent that we discussed. So black holes obviously will also make a dent. Now, as the dent is made, light, because it travels in this mesh, the light is also bent. So what happens is that this light gets bent and it gets trapped inside the black hole. It falls towards the black hole. All right. And secondly, mass, when it comes to light, we can also think of light particles. All right. So light also has particle nature, basically, like if you know about photons. So photons are said to be light particles. So these particles are the ones which are being trapped. These are the ones which are being trapped inside the black hole. Whatever we are looking at now in space, which is billions light years away, does it mean that those actions took place years back? You're absolutely correct, Lakshmi, that what we are seeing is something that might have happened millions of years back, and what we are seeing right now is a repeat telecast or of what happened. So we are in a manner looking into the past, looking back in time while we are looking at a star. So you are correct. Is singularity an infinite point of black hole? No, not an infinite point. It's a defined, very dense point that we have, or rather, an area or a region, you can say. LIGO is just, you can say, a radio. I mean, it's just a gravitational wave observatory and nothing else. This is where we have been able to detect the first gravitational wave. That is the significance of uh, LIGO. That's it. If we can't see black hole in with our bare eyes, even if it's close also, then why we can't say black hole as dark matter? Because see, it's not only about us not seeing. We have been able to detect black holes. We have known about the existence of black holes because it signifies absence of light, not absence of matter. We know that there is matter, we understand that there is mass, and we know about the presence of black holes. The problem with dark matter is that we do not even know about their presence. We are just, they exist in our calculations only, that our calculations say that there is something wrong, so okay, there must be dark matter. So that's not the case with black holes. We know about black holes, we know that black holes exist, we know that they are formed when the stars die. That's not something that we know about dark matter. We do not know where they are formed from, what they are, how they are, what their properties are. We do nothing. But in case of black holes, we know everything, just that we were never able to see them. But with now the event horizon telescopes, we have been able to even see that. What is white hole? White hole basically is a hypothetical concept where we are talking about something of a reverse concept, where light, energy, everything can escape from one single unit or one single region, and they can go out. So that is basically how we define it in case of white holes. But hypothetical concept, because if you apply the laws of thermodynamics to it, white holes cannot exist. I mean, they are not real concepts. Gamma ray bursts. Gamma ray bursts basically are bursts of gamma radiations that we have seen in various different aspects of various different points in space, where very suddenly, within milliseconds, we see that there are bursts of gamma rays that happen. Again, we have very little knowledge about them. What is the environment inside a black hole? See, what we only understand is that the mass is very high, the amount of mass is very high in a very concentrated manner, meaning that density is very high because volume is very low and mass is very high. So you have, just imagine that you have thousands of suns worth of mass, thousands of suns worth of mass, maybe just in 100 kilometers or even 20 kilometers range. So 20 kilometers having mass of almost hundreds of suns is unimaginable for us, and that is what exactly is the scenario there. If there is a black hole, if there is a black hole, then all the light rays of the sun should be trapped. Then why Earth has light? No, sun does not have a black hole. We just discussed that there is no black hole. I mean, if there was a black hole in the vicinity, we would have been sucked inside it. So we do not really have a black hole near the Earth. Does gravitational wave make distortion in the universe? Quite opposite. You can say that gravitational waves are mm, created or formed because of the distortions. They don't create the distortions. They are formed because of the distortions. What is a celestial body? Any body that is found in space is called as celestial. Anything that is found in space. Size of black hole can be just 10, 20 kilometers to up to 50, 60 kilometers. Black holes have comparatively more mass. Now depends on what you mean by comparatively, because mass wise they obviously will have the mass of not only the star, but rather than everything that is in the nearby vicinity also. So that's why, um, in that sense, saying something about it is very, very difficult. All right, so let's move on. Is UPSC and civil services examination both the same? Oh no, UPSC conducts the civil services examination. UPSC conducts a lot of examinations, and one of those examinations is the civil services examination for which you are preparing. Please know these basics. I should not be the one telling you about these basics. All right. So, coming to the sun. Now, sun, we know that sun also is a star, an average star, average size star. That's why also called as a main sequence star. So the meaning of a main sequence star is that these are average stars. Now, why main sequence? I'll not go into that. Um, that's beyond our requirement. So these are average stars. Now, when it comes to the sun, we know that first, to understand the sun has various regions. Just for example, how you know about the earth also, that we have a core, a mantle, and a crust. Similarly, the sun also has a core, and core is where all the nuclear fusion happens. This is where nuclear fusion takes place, and hence this is what becomes the source of heat and light. Source of heat and light of the sun. So source of heat and light of the sun is the core. Now that's why the core temperature also is very, very high. The temperature can be easily in the range of 15 to 20 million degrees Celsius. 15 to 20 million degrees Celsius would be the temperature at the core of the sun. Now, as we move out of the core, we come across these two zones called as the radiative and the convective zone. And these are the zones which are just connecting the outward of the sun to the inward of the sun. And all the particles, all the plasma, all the charged particles, light, energy, all these are being sent outwards through these zones. Then after that comes the photosphere. Photosphere is like the surface of the sun. This is like the surface of the sun. And now that we have come to the surface of the sun, it means that the temperature has dropped, because now you have come away from the source of heat and light. So temperature should drop, and that is what happens, that we see that the temperatures would be in the range of almost 5500 to 6000 degrees Celsius. So temperature is 5500 degrees Celsius or near abouts at the surface of the sun. And that's very obvious because now there is no source of heat and light at the surface, and that's why the temperature has dropped from almost 15 to 20 million degrees Celsius to just 5 to 6000 degrees Celsius. Then outside this is the atmosphere. As you can see, that from the core we come to the radiative and the convective zones, then the photosphere, and then lastly the chromosphere and the corona. So chromosphere and the corona, they basically together form the atmosphere. They form the atmosphere of the sun. Now these two regions, they are the ones that will be also visible whenever any eclipse happens. So whenever solar eclipse happens, you might have seen that a ring like structure is visible, right? A reddish colored ring will be visible all across the sun. This reddish ring which is visible is basically the corona of the sun. So this is basically something that is visible during total solar eclipses. So during total solar eclipses, you see a ring-like structure, that is the corona. Do you know what is the meaning of corona? We had the coronavirus also in news, and I mean everybody has heard of coronavirus. But why corona? What is the meaning of the word corona? Yes, crown. Corona means crown. And that's why, because on the surface of the virus, you have those spikes. So those spikes are like the crowns of the virus. And that's why the name coronavirus. And similarly, in this case also, the reddish ring like structure that we see, that is like the crown of a king. So that's why the name corona has been given to this outermost part of the atmosphere. Now, here in this, there is something very unique that happens. As we come out of the sun, the temperature of sun should drop further, that from 5 to 6000 degrees Celsius at the surface. As you go outward, the temperature should be even lesser, right? Temperature should be less than 5000 degrees Celsius and so on. But opposite of that happens, that when you are at the chromosphere, the temperature of the chromosphere can be up to 50,000 degrees Celsius, and the temperature of the corona can be 1 up to, let's say, 1 million degrees Celsius. 1 million degrees Celsius. So temperature that should have dropped further, because there's no source of heat or light, temperature that should have dropped further does not drop but rather rises. So temperature first drops and after photosphere again rises. Why does this happen? Thankfully, we don't know. There are various theories that this might be the reason or that might be the reason, but good for us, or probably good for you, that we don't know the exact reason to why this sudden rise in temperature happens. So because of this sudden rise in temperature, we basically say we observe this as an anomaly of what's happening inside the sun. And that's why we want to understand what's happening. And that's why there are missions. If you have heard of the Parker Solar Mission, or the Parker Solar Probe, which was launched a few years back, it is trying to study the atmosphere. And then our own Aditya L1 mission. So Aditya L1 mission also will be trying to study the atmosphere. So these are all trying to study the atmosphere so that we can understand what's happening here. What's the exact reason? Why these are all these phenomena and what's happening with all these phenomena? We are trying to understand all that. And that is where we see that all these regions of the sun, they become crucial. Now, when it comes to the sun, there are certain concepts which are very, very important with regards to the sun. And this is where we have three very, very important concepts: sunspots, solar flares, and solar winds. So we'll try to understand what do we mean by sunspots, what is solar flare, and what is solar wind. Now first, sunspot. So if you look at these pictures, you can see that there are spots that you can see on the surface of the sun. So these spots are called as sunspots. Now, why these spots? What is the reason? What is the origin of these spots? Now, these spots, although they look like spots from where we are seeing them, but these are not spots. These are very big regions. These are very big regions that you have on the surface of the sun, and they are characterized by lower temperature as compared to the surrounding areas. That's why they appear darker. They appear darker because they have lower temperature as compared to their nearby areas or the vicinity. So temperature range could be in the range of 3500 to 4500 degrees Celsius. Whereas as we discussed that the surface temperature of the sun is in the range of 5500 to 6000 degrees Celsius. But here the sunspots will have lower temperature, and that's why they appear like a spot on the surface of the sun. And these are observable from the earth. If you have very good resolution cameras, if you have uh, very high resolution cameras, you don't even need a telescope many a times to see these sunspots. Interestingly, a couple of months back, I was able to observe a sunspot through my phone camera when I because it was very densely foggy and the sun was visible very easily, and it would not have hurt uh, the lenses of the camera. So I zoomed into the sun, and interestingly, when I was processing the image, I was able to actually catch a couple of sunspots. So that was a big thing for me that I was able to catch a sunspot while taking that picture. So sunspots, basically, just understand this, that when it comes to the sunspots, these are dark, cooler areas that appear on the surface of the sun, and they are temporary phenomena because of intense magnetic activity in the sun's photosphere. The surface temperature, as we discussed, surface temperature is between 3500 to 4500 degrees Celsius, and they will be formed because of the concentrated magnetic field lines that poke through the sun's surface. So they will basically, what happens is that magnetic particles, they will basically be coming out of, or they will be lodged from lodged outward to from the surface, and they leave behind blank areas. They leave behind a kind of a vacuum, you can say, of particles, and because of that they appear as darker areas, because these particles have left the surface, leaving behind darker spots. So that's why we call them as sunspots, and this is basically what happens in case of sunspots. So then inhibit the convective flow of hot plasma, and they result in lower temperature and reduced energy emission. Now one thing very very important, they follow something called as a solar cycle. Sunspots follow a solar cycle which lasts for 11 years. So sunspots, they, so if, for what we mean by solar cycle is that if the spots have appeared here today, then 11 years later, exactly the same spot, exactly the same region, you will see the reappearance of the sunspots. So that's why we say that they follow a 11-year solar cycle. All right. So 11 years later, if they have been observed here today, then 11 years later, again, they'll be observed here itself. So that's why we say that they follow a 11-year solar cycle. Then apart from sunspots, another very, very important concept is of solar flares. Now, if you look at this picture, what you see is that outward there are flares which are coming out of the sun. And if you look at this picture, you'll see that this kind of a big flame kind of a scenario, big flame is coming out of the sun. And this is so big, if you look at the scale of the earth, compared to the earth, these are very, very big flames or flares which are coming out of the sun. So, in a manner, you can say that it is a sudden burst of energy, a sudden burst of particles, sudden burst of charged particles and magnetic particles which are released from the sun. So that's why they are called as solar flares. These are called as solar flares. Now, in case of solar flares, In case of solar flares, they basically, that's why we say that these are like big explosions. These are like big explosions that happen on the sun's surface, and they occur in the outer layer. So the origin, you can say, is in the surface, but they are visible in the corona. All right, they are visible in the corona. So they are visible in the corona. So start from surface, that is photosphere, but visible in the corona. All right, so what we see is basically corona. So we are actually able to see the corona. This is where we are able to see the solar flares. Now these solar flares become very, very crucial because they also help us in understanding of the sun. They help us in understanding of the sun's magnetic energy and how sudden release of magnetic energy from the sun can happen. And a lot of charged particles are released. So as you can see, that X-rays, ultraviolet light, or sometimes charged particles like protons and electrons, these are all released. So there are a lot of energy and radiation particles that are released as solar flares, and they can actually last from a few seconds to a few minutes to a few hours as well. And whenever this sudden burst of energy happens, it can have an impact on the earth also. It can have some negative impact on many of our instruments as well. And they also create some natural phenomena like the auroras, and we'll discuss about them as well. The third phenomena is of solar winds. Now, solar wind basically is a continuous flow of charged particles, and that's why remember the difference between solar flares and solar winds. That in case of solar flares, we are saying that solar flares are sudden burst of energy, right? Sudden release of energy. Whereas in case of solar winds, we are saying that these are continuous release of energy, right? These are continuous release of charged particles and magnetic particles. So that's the basic difference between solar wind and solar flare. So solar winds, these are constant flow of charged particles, right? These are constant flow of charged particles, and there it was sudden release of energy or sudden release of particles. That's the difference. And primarily composed of electrons and protons, but also have heavier ions which can be mixed. And overall, they are also emitted from the corona. And overall they can also lead to increase in the intensity of the magnetic field, because all these charged particles, they have magnetic properties. Whether solar flares or whether solar winds, they all have magnetic properties, and that's why they can also cause some challenges to the earthbound systems as well. So when it comes to the earth and their effect on the earth, if you know about this, about what we call as auroras, or specifically this is a picture of aurora borealis. So there is aurora borealis, and then there is aurora australis. Seen these pictures? Have you seen these kind of pictures? And especially this year, it is pretty much more in news, because the observation of these green colored light that you see, these are largely uh, visible in the north and the south poles. So that's why aurora borealis. Aurora means what? uh, and aurora and borealis, right? And other way you have aurora and australis. So understand the meaning. If you break down the meaning of the word, you will understand what we exactly mean. So when it comes to the meaning of aurora, so aurora basically means that we are talking about light, correct? We are talking about light. So overall, when it comes to light and when it comes to the understanding of this light, so aurora borealis, borealis because it is in the boreal region. If you have heard of the boreal forest or the boreal vegetation, so what we mean by boreal is arctic. Arctic areas are called as boreal areas, and that's why the Arctic vegetation is called as the boreal vegetation or the boreal forest. So when we say aurora borealis, it means that these are lights or colors which we find in the Arctic areas. That's why aurora borealis. And similarly, aurora australis, because this is visible in the southern areas near Australia or the southern parts of Australia, and that's why aurora australis. Now, these basically are formed with whenever interaction between sun's magnetic field happens with Earth's magnetic field. And that's where the poles, that's where the north and the south poles, because north and the south poles is where you have the intensity of the magnetic field on the Earth. And that's why they are visible largely in the north and the south poles. So they are basically, both of them, they are created when magnetic field of the Earth interacts with the magnetic particles magnetic particles released by the sun. Right, so that's why both solar winds and solar flares both can lead to the formation of these auroras. And apart from that, I mean, solar winds and solar flares do not only cause auroras, they can also have negative impact on anything that is an electrical, electronic, or magnetic system. So whether these are aircrafts or satellites or communication systems or power systems, power outages have happened. Last year, you'll see that power outages were reported in New Zealand because the solar activity was very strong. Solar flares were very strong. So that led to power outages as well. So power outages can happen. Communication systems can be negatively impacted. Even aircrafts which are that are flying during the intensity being high, they can be impacted. Satellites can be impacted. All that can be negative impact. But these beautiful lights, these are the positive impact. And this year, I mean, if you know, I'm not sure whether you know this or not, 2024 specifically and also 2025, these are supposed to be years of solar maximum, meaning that the intensity of solar energy or solar magnetic particles are going to be very strong this year and the next year. So if you are interested and if you have enough money, then in that case you can go to the north polar countries, go to Norway or Finland or Denmark, Iceland or Alaska, etc., Greenland if you can. Then these areas, if you go, you will find these kind of wonderful pictures. But uh, but you need to have enough money to do that. So, and also time, because you are also preparing for this examination. You cannot just leave your preparation and just go and start watching it. Instead, go and watch it on YouTube. Right. So with this question, this was asked in your 2022 paper. I launched the poll for you. Please mark your answers. Hmm. Good. So 64% of you have marked C, which is actually the correct answer. So the question says, if a major solar storm or solar flare reaches the Earth, which of the following are the possible effects on the Earth? So what we discussed is that electrical, everything electrical, electronic, or magnetic can be negatively impacted. Now look at the options. First is GPS and navigation systems could fail. This is correct. We discussed that satellites can be impacted, communication systems can be impacted. So yes, GPS and navigation systems, these are electronic systems, so they can fail. So these are electronic systems, so hence they can fail. Second, tsunamis could occur at equatorial regions. Now, first we are talking about equatorial regions. Understand this. What we discussed is that magnetic intensity of the Earth are stronger at the poles, north and the south poles. So, does it have a lot to do with equator? The answer is no. Secondly, tsunamis. Tsunamis happen largely because of seismic regions, right? There are seismic regions because of which tsunamis would occur. It's not magnetic, right? It's not because of any magnetic particle coming from the sun. So that's wrong. Tsunamis cannot occur due to magnetic storm or a solar storm. Now, basically, you get the answer from here itself. The answer has to be C. Third is power grids could be damaged. This is also correct. We discussed that anything electrical can be impacted, and last year also it was in the news. It happened in New Zealand last year. Intense auroras could occur over much of the earth. Even this is correct. If you remember last year, this was very unique that last year, even in Ladakh, for the first time, it so happened that in Ladakh also auroras were observed because intensity of solar winds or solar flares rather were very strong. So yes, this is also correct. Forest fires could take place over much of the planet. Forest fires. Now here we are talking about magnetically charged particles. We are not saying that the sun is blowing a torch. It's not that sun is throwing flames at the earth. That's not the case. Magnetic particles reach the earth. And if that was the case, and for forest fires to occur, the heat intensity has to be very strong. But heat intensity is not strong. Magnetic intensity is strong. So that's why this cannot happen. And if it was so, it would not only be forest fires, we will all be roasted. So don't worry only about the forest in that case. That's wrong. Orbits of the satellites could be disturbed. That's correct. We discussed that anything electrical, electronic, or magnetic can be disturbed. So yes, this is also correct. Shortwave radio communication over of the aircraft flying over the polar regions could be interrupted. This is also correct. Especially it talks about polar regions of the radio communication. So yes, this is also possible. So only 2 and 5 are wrong. So correct answer will be 1, 3, 4, 6, and 7. Any questions if you have? We'll not start the new topic because I think you have the webinar also today. So take a 5-minute break before you go to the webinar. And I hope you go to the webinar. Please don't skip the webinar, attend it. These are very important concepts that we discuss there. So yeah, any questions if you have? In case of solar winds also related to electrical and magnetic, yes. I'll write it here so that you don't confuse. Both both solar vents and flares can lead to electrical, electronic, or magnetic interruptions. Hmm. Aurora happen only in the coolest places. You can't say that. It will be visible wherever you do not have light pollution. Now, why Ladakh? Because Ladakh does not have a lot of light pollution. It's away from larger population, so that's why they were observed. And also, they will be observed in the areas where magnetic intensity is higher. So that's why the polar areas. So nothing really to do with temperatures as such. If we enter the black hole, what will happen? You will wish that you never entered there. You will be stressed and probably you'll just disintegrate into thousands of pieces. Does both solar winds and flares cause auroras? Yes, exactly. That is what we just discussed, that both of them will cause the same thing. Is solar flare harmful for the earth? Only, as I discussed, that only for the communication systems which are magnetic or electronic in nature, they will have a negative impact. How much megapixel mobile camera is required with regards to solar? It's not really about megapixels on your camera. Megapixel is a different story. It's more of a marketing gimmick than anything else. It depends on the camera more. It depends on uh, overall when it comes to your camera composition, what the aperture size of the camera is, what how much of focus can the camera do, what is the distance that it can take pictures in. There are a lot of factors that come in, and how basically when it comes to the pixels, what is the overall uh, average number of pixels that it can distribute its picture into. So all these things will matter, the sensor will matter, there are a lot of things that matter into taking these kind of pictures at all. In other ways also it is harmful or not? Not really, not really. Does multiverse really exist? Have we been presented in the other see, a multiverse right now remains as just a theoretical concept. There is not a lot of scientific evidence that supports the theory of presence of multiverse. Webinar happens only in the evening time. Yeah, webinar happens at every Tuesday and Thursday, 8:30 in the evening. A lot of you are asking about my phone. I have a Samsung S23 Ultra phone, which was used to capture that image. What is a strange matter which people call the most dangerous substances in the universe? Uh, See, strange matters are more speculative than anything else, because strange matters are supposed to exist inside the core or inside neutron stars, for example, made of quarks and made of some of the other subatomic particles. So that is more of an hypothesis, you can say, more than anything else. And why, I mean, since you have talked about why dangerous because if the collision of strange particles or strange matter happens, they can create or they can actually generate enormous amount of energy that can be dangerous. So that's why it is said, but again, overall it's more of a hypothesis than anything else. A solar eclipse is dangerous? No, we can't say that. It's just a natural phenomena. Can I leave the class? Yes, you can. I mean, there are new concepts not to be discussed. New concepts we'll discuss tomorrow. So I'm just answering all the questions that I see here in the chat. Right. So I think I've answered all the questions. Anything else? Can gamma ray bursts lead to mass extinction? Very difficult to say that, because gamma ray bursts are largely happening not in the solar system. I mean, millions of light years away. They have been detected from. So no, not a direct relation between the two. What is aperture? Aperture basically you can say is the opening of the camera. The larger the aperture, the better light it can take in. So that's why, for example, if you have to take pictures in darker regions, so for example now we have night vision cameras and the cameras in the smartphones also, which can take pictures in relatively dark environments. That happens because now we have cameras which have better apertures, bigger apertures, so they can let more light come into the camera, and that's why they are able to take pictures even in relatively low light. So aperture is nothing but the opening, how much opening the camera makes so that it can let the light enter it. Hmm. So let's end the class here. So if you have any further doubts, you can again bring them back tomorrow. Please go back, revise everything. If you have any doubts, we can have a discussion tomorrow. Thank you very much and good night. Good night for me, but not for you. Please go and attend the webinars.